Funding for this program is provided by Annenberg CPB to advance excellent teaching.
Newton's second law, F equals ma, combined with a restoring force, leads to a motion that repeats itself over equal periods of time, producing what is known as harmonic motion.
I have a story to tell you. I'm not sure that it's true, but it's a good story, so I'm going to tell it to you anyway. It's about our old friend Galileo. One day, when Galileo was a young man in Pisa, he attended Mass at the Duomo. That's the magnificent cathedral in Pisa, whose bell tower is the famous Leaning Tower of Pisa. In the Duomo, there's a lamp that hangs down from the ceiling by a long cable. And on this particular day, the lamp was swinging back and forth. Probably it had just been lighted. And Galileo, being Galileo, noticed something about the swinging lamp that no one had ever noticed before. He noticed that each complete swing of the lamp took exactly the same amount of time. When the lamp first started swinging, and it had a large arc, it moved quickly through the arc. Later on, when the swinging had died down and the arc was smaller, it swung more slowly through the smaller arcs. But the total amount of time for each complete swing was always exactly the same. How did he determine that? Well, he timed the swings by counting his own pulse. I've often wondered about that, having realized that he was making a great discovery, why his pulse didn't start racing and ruin his own measurement. But in any case, he timed his own pulse. Now, I figure each complete swing of that lamp must have taken about 5 or 6 seconds, and he had to watch it go through many, many complete swings as the motion got smaller and smaller, counting this pulse each time to make sure that each swing took the same amount of time. It must have been a very dull sermon. The lamp is still there in the Duomo in Pisa. It's called Galileo's lamp, and for a few hundred lira, you can buy a picture of it from the enterprising street vendors outside on the piazza. And so you see, it really is a good story. The only thing wrong with it is that according to the church records, the lamp wasn't installed until 10 years after Galileo died. But Galileo really did make that discovery, and it was extremely important, because what he had discovered was that a pendulum could be used as a timing element. And in fact, his discovery led immediately and directly to the invention of the first accurate clocks. The kind of motion he was studying is called simple harmonic motion.
Bobbing up and down on an ordinary spring, this simple weight repeats itself once every second. As time passes, its motion dies down, its excursions become smaller. But it still takes exactly 1 second to make each cycle. It is a perfect timekeeping device. And its motion is called simple harmonic motion. Keeping time has a musical connotation, as does the word harmonic. That's no accident of language. Instruments share a special property with bobbing weights. Both generate vibration at a certain frequency, which produces a certain pitch that doesn't change as the motion decreases. Many factors are at play in the production of musical tone. The length of an instrument's string, the size, and the shape of an instrument. The technique with which an instrument's played, and certainly the musician's ability to play it. However, in the physics of music, one factor never varies. Once the tone has been produced, the pitch remains the same, even though the vibrations diminish. Why does the pitch remain constant? In the language of classical mechanics, force. The F in Isaac Newton's F equals mass times acceleration.
In a certain position, all forces are balanced. However, when the spring is stretched, it attempts to pull the mass back to its original position. The farther the mass moves, the greater the force to pull it back. The same principle works conversely. When the spring is compressed, it tries to push the mass back. Whichever direction the mass moves, a force emerges to counter the displacement. The combination of this force and the mass's inertia will be the key to keeping time. At each point in its motion, the net force is proportional to the distance x of the mass from its equilibrium position and in the opposite direction. The equation is F equals minus kx. The value of k depends on how stiff the spring is.
In Western culture, few things govern human life as steadily as the mechanistic concern with time. Although advancing technology gives more people more time on their hands, there seems to be a constant need for increasingly accurate timekeeping devices. Preoccupation with time isn't a phenomenon of the fast-paced 20th century. It developed gradually, hour by hour, day in and day out for thousands of years. Accurate time, however, came relatively late in history. It arrived with the physical principle of harmonic motion. And along the way, over time, harmonic motion became the only means of timekeeping accuracy. But it's time to go back to the beginning. How did the concept of time develop? Perhaps from witnessing the cycles in nature, the changing seasons. Perhaps from noting the annual solar or monthly lunar cycles. Many early civilizations built monuments that suggest insight into the cyclical movements of the sun, moon, and earth. These structures mark the passage of time on a broad scale. Early calendars represented efforts to segment annual cycles into smaller increments. Sundials divided a day, unless it was cloudy. About About 500 years after the advent of the sundial, the Egyptians developed the water clock. The dripping water revealed successive lines within an alabaster bowl. This basic design remained unchanged for centuries, until Chinese artisans improved it by adding small wheel-mounted cups and a trip lever. After Marco Polo spread the word from the Orient, semi-mechanical clocks enjoyed considerable popularity in 13th century Europe. Unfortunately, European winters freezing the water clocks in place often made time stand still. When introduced in the 14th century, the sands of time didn't freeze. However, because of the bulk of the sand, such clocks were limited to measuring short intervals. Around this time, the first mechanical clocks were introduced. They had moving parts, including pulleys, weights with escapements, gears, and trip levers. Often they were ornate, delicately crafted timepieces, and always their accuracy varied according to the skill of the craftsman and the quality of the materials they had at hand. Early mechanical clocks were further improvements, but time still wasn't something people could exactly count on. The length of an hour depended on whose clock kept time. Day follows night. Season follows season. And year follows year. The Earth's endless motions following the inexorable laws of the mechanical universe mark perfect time. Every human-made clock is an attempt to imitate nature's precision. No matter how ingenious, ancient water clocks, sand clocks, and mechanical clocks ultimately failed to keep accurate time, at least for any length of time. Why? Because they neglected to imitate one essential aspect of nature's clock: the cycle. Time and nature are cyclic. Day and night, winter and summer, the cycles repeat themselves endlessly. Ranging from a microscopic cell to the rotations of galaxies, nature repeats herself in oscillations. There are natural cycles. The beating of the human heart, the frozen pace of the advancing and retreating glacier. And there are perhaps less natural cycles, such as the boom and bust of the economy, and other things that tend to rise and fall. However, these cycles don't operate under the same laws that govern nature's great clock. They don't oscillate with natural precision. They lack precise intervals, repeating forever according to an inexorable law of nature. Human imitations of the great clock of the heavens are based on a different but equally inexorable law.
The most inexorable law in mechanics is F equals m times a, the second derivative of x. In simple harmonic motion, force comes from the displacement x itself. F equals minus kx. Together, these two equations give the differential equation that describes simple harmonic motion.
That differential equation refers not only to a mass on a spring, but to any physical system that, when disturbed, is restored toward equilibrium with a force proportional to the disturbance. For example, the pressure of the air in an organ pipe, or the angle of a pendulum, the bending of a tuning fork, or the rotation of a clock movement. These systems and many others undergo harmonic oscillations. These oscillations can be too fast to see, at least under normal circumstances, or too slow to wait for. Or they can be any other frequency, high or low. No matter the frequency, however, they can all be described by the same differential equation. The differential equation is solved by the time-honored technique of guessing. A long time ago, someone guessed that the solution may be a sine function. It was an educated guess, because the motion of a mass oscillating on a spring resembles the motion of the shadow of a particle moving in uniform circular motion. So the idea of guessing a sine function seemed quite natural. In this case, a sine function with amplitude A and angular frequency omega. But if that's x, is its second derivative equal to minus k over m times x? The answer is yes, if omega is chosen correctly.
For the mass on a spring, the angular frequency is equal to the square root of k over m. The stiffer the spring, the higher the frequency. The greater the mass, the lower the frequency. But whatever the frequency, it depends on the mechanical properties of the oscillator, such as the mass and the spring constant. The time needed to make a complete cycle does not depend on how big the swings are, represented by A in the equation for x.
So even as the oscillations die down, harmonic oscillators continue to keep perfect time. The frequency is measured in radians per second. There are 2 pi radians in each complete cycle. Likewise, in the great clock in the sky, each cycle is divided into radians, as if the universe were an enormous circle. To an extent, it is. The natures of uniform circular motion and simple harmonic motion are closely related. Each clock, in its attempt to duplicate the cycles of nature, is a mere shadow of the cosmic clock. Just as uniform circular motion and simple harmonic motion shape up much the same in nature, the potential energy of harmonic motion can be visualized as a curve shaped like a bowl. Why this shape? Because of the force law and the definition of potential energy. The ball starts out with some potential energy. As it rolls toward the bottom, the potential energy changes to kinetic energy. As it rolls up the other side, the kinetic energy changes back into potential energy. Over time, there's a continual interchange between kinetic and potential energy. But even though both the potential energy and kinetic energy are always changing, the total energy is always constant. When any harmonic oscillator is disturbed, the disturbance produces a force that pushes it back to where it was. There, the force is zero, but inertia keeps it going until the reverse force stops it and pushes it back once again. This is the essence of harmonic motion. A simple harmonic oscillator. If it were really simple, it would go on forever. A perpetual motion machine. But real oscillators are not simple. they always have other forces, friction, air resistance, and so on, that tend to make them slow down. That's why from time to time, clocks must be wound or have their batteries changed. Friction turns energy into heat. That energy must be restored in order to keep the clock going. But even as the clock winds down, the period of time for each of its cycles remains constant. That fact, and much more, was first discovered by Galileo Galilei. His timely discovery, which stepped up the pace for improved timekeeping in the Renaissance, was summarized in 2 new sciences. In that work, Galileo observed that a pendulum takes the same time to complete each swing, even though its motion dies down. Galileo also observed that all pendulums of the same length oscillate at the same rate, regardless of their mass. Of course, Galileo, who discovered the law of falling bodies, realized that a pendulum itself is a falling body. If all bodies fall at the same rate, regardless of their mass, then all pendulums of the same length should oscillate at the same rate regardless of mass. Why doesn't the time of the pendulum swing depend on its mass? Isaac Newton answered that question. Thanks to Galileo's law of falling bodies, Newton realized all objects fall to the Earth's surface with the same constant acceleration. Then, from a conceptual point of view, he saw a connection between, for instance, pendulums of different masses and freely falling bodies. The force of gravity, which depends on the mass of the pendulum, can cancel the mass in the equation F equals ma. In a sense, then, by using pendulums of different masses, Newton tested the law of falling bodies without the advantage of a vacuum. Thanks to Newton, not only physics, but the nature of time itself was never perceived as quite the same. With harmonic oscillators, clockmakers were able to introduce accuracy and uniformity to timekeeping. An hour in Cambridge became precisely as long as an hour in Venice.
Don't worry, you'll be in the water soon, love. Over here.
Accuracy proved a boon to navigation. In determining longitude, navigators needed to bring along an accurate clock that kept precise time with Greenwich, England, the point of 0 longitude. Sailors could tell local time from the position of the sun, and knowing how that compared with Greenwich time, they could determine their longitude. But an error of only a minute could put them many miles off their course, or even get them lost at sea. The same harmonic motion that regulates the accuracy of a grandfather's clock is the principle behind the accuracy of modern quartz watches, where millions of oscillations per second keep incredibly precise time. Harmonic motion can be found in an enormous variety of physical phenomena. Understanding it helps to explain the subtle unifying principles that govern the universe.
Do you remember our discussion of stability? For an object to be stable, it must have no net force on it. But in addition, if I disturb it, that must produce a force that pushes it back to where it was. What we've studied today is the motion of a stable object. Whether it's a mass on a spring, or a pendulum, or a rolling ball, if I disturb a stable object, it executes simple harmonic motion. When I was a student, I studied simple harmonic oscillators just as you're doing. I went slogging through all the sines and cosines. You had to do it to pass the course. But I couldn't understand why. It seemed to me like more examples of pulleys and inclined planes. But then as time went on, I began to see more and more examples of completely different systems, all of them executing the same simple harmonic motion. Not just masses on springs and pendulums, but organ pipes and electric circuits, and even atoms in a crystal lattice. And then I began to get the point. Simple harmonic motion is nature's response to twanging any stable system. That's why it's so important. But that's not the end of the story. It's just the beginning, as we'll see next time.
A linear restoring force, F equals minus kx, leads to simple harmonic motion when inserted into Newton's second law. The solution to the differential equation is the distance from the equilibrium position, expressed by x equals a sine omega t, where a is the amplitude of the motion.
Funding for this program is provided by Annenberg CPB to advance excellent teaching. For information about this and other Annenberg CPB programs, call 1-800-LEARNER and visit us at www.learner.org.